Good. Welcome to this edition of the 3DGV seminar. It's my pleasure to introduce Niloy Mitra. He's a professor of geometry processing in the Department of Computer Science in the University College of London. And he's also a principal scientist at Adobe and is running the Adobe Research Lab in London. He received his master and PhD in electrical engineering from Stanford under the guidance of Leonidas Guibas and Mark Niloy. He was a postdoctoral scholar with Helmut Pottmann at the Technical University of Vienna. His research interest is in representing, reconstructing, analyzing, processing, editing, and fabricating 3D shapes for computer graphics and vision applications. He's known for his work in local and global orchestration, symmetry and regularity detection, structure-aware geometry processing, and functional modeling for fabrication applications. His current research focuses on developing machine learning frameworks for generating high-quality geometric and appearance models for computer graphics applications. And with that, yeah, it's my pleasure to look at Niloy's talk.
Thanks, Thorsten, for the very generous introduction. And thanks for all the organizers to the seminar. I think in this COVID times, it's quite a privilege to be able to attend a coherent set of seminars and get to listen to really interesting talks on various angles looking at this problem. So today I will talk about something we have been focusing on for the last several years of how to create 3D geometry and along with the material, and I would explain different aspects of it. And I will explain what I mean by deep here as we go further in this talk. Okay? So let me start with the problem that we have. And I think it's a very relevant problem in the sense it's important because there's a lot of applications, but we don't have quite the easy solutions right now. So we'll start with this. So suppose I want to create geometric assets that represent a full scene. And by this, there are several things we have to do. We have to get the objects in terms of meshes, in terms of point clouds, in terms of NURBS patches, so whichever representation you want. We want to get their arrangement right, so the relative placement of the object. They have to be semantically correct, they have to be correct functionally, and we get the right materials for it. Once we can get this, then we have very realistic rendering engines that can produce really spectacular renderings of these scenes. And this is only showing a static scenes. Imagine this being dynamic, and then the type of usage can be from training neural networks for several supervised tasks to doing design planning and AR/VR applications. So that's the eventual motivation. But what are the real challenges in realizing this vision? So if we look at the 3D model here, and I pulled one of the models from the 3D stocks from Adobe Assets, the visual complexity of the model is very high. And this is manually created by an artist with hours of effort. But there are certain things that makes it difficult. First thing that will come up in many of the things I will talk about today is what is the right representation? Is it a sign distance field? Is it triangle mesh? Is it point cloud? Is it something we'll scan or something else? Then how do we capture the geometric variations, which is often continuous, to the topological variation, whether it's a chair with 4 legs or a bar stool with a single leg, etc. How do we capture the material properties of it, the BRDF of it, or even the surface detail at the meta level, or the micro level? Is it something we will procedurally model triangle by triangle, or we will scan directly and each one has its pros and cons? Then one thing that turns out to be one of the biggest challenge here is where do we get large volumes of 3D training data? And this is, I do not have an answer to this. So we'll see how we can avoid working with direct 3D training. And finally, the last part of the talk, I would like to ask a question, which is a bit provocative, which is, for certain application, do we even need explicit 3D in terms of representation, or is it enough to enable the controls that we care about? Okay. Now, let's see what's going on in the industry right now, in the gaming industry. So this is a slide I borrowed from Andrew Price's talk, which is showing the scale of the problem. To create a very, very high quality geometry, whether it's for a game or a VR environment, it takes hours of very skilled person's effort, which easily amounts to several thousands of dollars to several $100,000 if we are talking about a single environment, in this case, the street facade. And it just does not scale if we then have complexity of motion, etc. Now, we have shown that this is an important problem, this is a relevant problem, but the current bar is too high in creating 3D models at scale. And we really want to enable these various aspects of it. The content should be real and functional, should be controllable, and should be editable or changed quite easily by intuitive user control. So that's the agenda we have. As a preview of a result, in case of supervised assets, where we have supervision in case of annotated 3D content, annotated image facades, we showed a couple of years back that it's possible to create very realistic 3D facades with details along with textures. So this is a reconstruction around the area of my office in London for a several square kilometer of area. Now, such a method requires supervision at many scales, at the level of 3D assets, at the level of facade fronts, at the level of images, at the level of from where the cameras were placed while taking the images or the LiDAR scans, etc. This avenue does not scale very well because of the complexity of the acquisition process. So let us take a different avenue. Right. So let us start by, if we have somehow created models, can we create topological variations and geometric variations? Can we create more instances? So this is the first set of work I will talk about that we presented last year at SIGGRAPH Asia and a follow-up this year at CVPR, which is a work where we created a coherent representation that combines geometric and topological aspects. In the teaser here, you see a chair with different parts, different number of legs, leg braces, etc. And this is what we call structure, which is the connectivity of the parts of an object. And this comes in many areas in graphics, if you call a layout, if you talk about patterns, if you talk about scene graphs where the nodes are individual objects, to compositions, to even substance like material properties, very high quality materials that gamers and production people use. Now, all of them, if we directly work at the image level or point cloud level and do a form of latent encoding, then when we do interpolation in that space, we get kind of a blurry output where the individual parts are sort of lost. So if you look at this example here, it's unclear if the legs are connected by leg braces, if there's an arm of the chair, etc. As a preview of our result, what we enable with the structure net and the follow-up efforts is it's a part-based model that allows us to create interpolation in a space where the geometry and topology of the space have been combined. So parts appear and disappear as needed in a semantically coherent way. We were inspired to do this work by a follow-up of a GRASS paper that was presented at SIGGRAPH a few years before. But there they assume that the graph representation of the model is a binary graph. And I'll talk about that, why that's a restrictive assumption that we relax in this work. So let us summarize the challenges in combining geometry and topology, which is essentially combining continuous and discrete changes. Is there are going to be various number of parts without any explicit correspondence between the parts. So we have to encounter and handle this in the algorithms we will present. Once we can do this, we can create a latent space that allows us to take a variable from here and decode to a shape, and also take a shape and encode to this space. This is the agenda we have for the structured network. Now, this is inspired by our work over the last many years, where we have justified the use of part-based models and represented part-based models as a graph. And these part-based models can be obtained in an annotated data set or via semantic segmentation, where there's a huge body of work working on this. So the individual parts are the point cloud or the bounding box for each of the parts, but the real information is in the structure of the parts, of how are the parts connected, that we encode as a graph, where the edges denote their connections, their symmetry, and their regularity. This is a representation that we very strongly believe is the right way to go, because of the following. If we look at these two models and look at their structure, they look very different, because the left model have 4 legs and the right one has legs along with the leg braces, etc. But if they're hierarchically organized, the parts, then once we go up in the higher levels or the coarser levels of the hierarchy, there's a lot of similarity that we can explore and exploit. Okay, so our setup is we are given a graph, and it's not a binary graph, as you see. It can have 2 nodes, 2 children, 3 children, n children, or k children in general. The goal is we want to encode this into a latent space. So the way we would go is we will take subgraphs, in this case here, and combine them to form one component, and we will progressively take subgraphs and combine them until we reach a single node. Right? So that's going to be our algorithm. For decoding, we will go the other direction. We will start from the meta node, we will decode it, and progressively keep decoding until we reach the end. So that's the very, very high level intuition of the idea of the algorithm, but there are certain challenges in this process. First is, while encoding, we have to encode subgraphs. So that's one problem we have to solve. Okay. Then while decoding, we have to know when to stop. So when we have reached the leaf level node. The third problem is, if we look at the original graph and the decoded graph, you see that the order of the nodes may not be same. They may have a permutation in that. So our method or the loss function has to be invariant to this permutation. And finally, we might have 2 nodes as children, k nodes as children, etc. that we have to handle. To summarize or repeat them, so we have to encode, decode subgraphs. We have to have invariance with respect to ordering of the siblings. And we have to handle variable number of children, and we have to stop the recursion. So I will primarily focus on the first 2 aspects here. So to work with this, we rely on the graph network formulation, where we are taking the nodes along with the edge information. I will make it specific what we encode in the edges, and then we build a message passing network that passes the information and updates the features. So these are the starting features, and we have the edge connectivity, which is given by the hierarchy of the graph connectivity, and what is outputted is updated node features, which is how the training works in this graph network. Essentially, we are using the graph Laplacian for propagating the information and diffusing it over the graph. Okay. And what we are learning are the weight vectors, which associates the features over time, over iterations. Okay. Now, what about the edge information? So as edge information, we capture 3 types of information. We capture the adjacency C1, the relation between them, and explicit symmetry relations I will talk about. Now, each node has its feature that we start with from the T-1 iteration. And then we have this MLP, the H function, that takes the type of relation. So we have one for each type of relation and updates it. The MLP learns to update the features to go from t-1 to t. Okay. And this is how we update the features over iterations. And to handle the permutation of the nodes, we take the max function so that we are not relying on the ordering of this. So it can be seen as a generalization of the point network, which also maps point features to high dimensional features and then aggregates via max function. So this is solving part of the problem that we can go from a subgraph and encode to a feature vector. So this is a geometric encoding. So as I mentioned, we have reflective symmetry, we have the rotational symmetry. These are the two types of symmetries, along with translation. And then we have the adjacency one, like if the two parts are connected or not. Okay, so let's look at some examples of how this works. So given this chair along with the hierarchy, so we need the explicit hierarchies to start with. What we are going to do is we use this encoding that I explained, and that allows us to map it into this latent code from which we can decode. Now we have to define the loss function, and this composes of three terms. So we have a standard reconstruction loss that we can see here, which would be at the point level. So we use a chamfered loss. Then a component which is quite unique to StructureNet is we have an explicit graph level edit distance, which we call the structured loss, the structural loss. And there's a variational component regularizer because we are using a VAE. So the most relevant or the novel part here is the structure consistency loss because we have the explicit graph encoding of this. So this part I explained that we have the chamfered loss, we have the cross entropy of the part level, as well as their relations. And to handle the ambiguity of the ordering of the loss, so inside the network, we do a Hungarian matching to establish a correspondence between the nodes. Now, I want to stress that here the hierarchy helps because the Hungarian matching has to be done only between at the same level of the hierarchy and not across hierarchy levels, and that allows a significant reduction in the complexity of the algorithm. Okay, so here's our encoding on a specific visual example. So we have the geometric encoding, so that is the starting features, and then this information gets aggregated using the graph network to lead to the final features that we get here. In the decoder, we go the other direction, and there is a truncation condition that I'm not going to mention in this lecture. Okay. There's a visual example of what we have seen before, but now with explicit instantiation of the geometry of the parts. So we tested it on the PartNet dataset, which is a geometric dataset with lots of geometric parts annotated along with the hierarchy given. And this hierarchy was the essential part to enable the algorithms. So the first one is how well does the reconstruction work? There's a validity of the method, and we indeed have very low reconstruction error and consistency error, as we see here. And you can look at the reconstruction of the StructureNet versus a point cloud-based one, that in the StructureNet, we get the part level encoding in a much better one in terms of numerical evaluation. It also does present much more reasonable output in sort of where it matches the input in a perfect sense. Both. So let's move to the most interesting application, which is the shape generation. So we can now sample from the shapes, and we can decode novel shapes along with their structures, along with their compositions of this. Okay. And here are examples of generations at the box level. You can also do this at the point cloud level. Notice the variability of the results in terms of number of parts, the legs, and etc. Interesting application because it enables a combination of the geometry along with the topology is we can now interpolate in the latent space and decode, which is a common application in a VAE space. But this allows us to do semantically interpolate between chairs. Notice how the number of parts change over the interpolation when we go from the left one to the right one. And here's a non-chair example, a bookshelf example, and you can also see the number of drawers or the cabinets appearing or disappearing over interpolations. So the main limitation here is we need this annotated data set with hierarchical components, and the output is pretty coarse in terms of the boxy abstracted structures. In the next part or improvement of this method is a work that is going to appear at SIGGRAPH Asia, where we take the structure net approach, but now we work directly at the level of programs. And I will talk about programs as what I mean by programs, which when executed gives shapes. So in the structured network, what we enabled was we can go from a sampling of the latency space to get a 3D object with parts and their relations, versus if you are using Maya or using Blender, you would have handles where you can change the parameters and directly get output of the chairs with height of the chair taller or shorter as you would want. So there are these explicit parameters that can control the number of back slats or the height of the back, etc. And what we set out to achieve is combining these two domains. Can we do a combination of two domains? That's what the shape assembly enables. It enables us to sample from this latent space. And when we sample, we get programs, which when executed gives these shapes. And then we can do changes in one of the two ways. We can directly interpolate in the latent space that allows us to generate programs as opposed to generating geometry before. And we can execute them to get shapes, but then we can also change the parameters of the programs explicitly to create a new chair. But the advantage here, as we will see in the evaluation, that this leads to much more semantically plausible and correct chairs or instances of objects. So the latent space in the left domain captures variability in terms of topological changes, where on the right, there is explicit control by changing the parameters of the program. This requires us to introduce a domain-specific assembly language. And this language looks a little bit strange on first sight because we came up with it, but you'd see the motivation later on that this language is specifically designed so that the subsequent learning is easier. So the first part of the language only produces a set of boxes, as you see on the top left. So these are a set of cuboids all around the center of the origin point. And all we care at these points are the size of the boxes or the explicit XYZ extent of the boxes. But then the shape is formed by two types of operator, by the attach operator, which says 2 points between box I and box J that are going to be snapped together in an axis aligned way. There can be operations that requires 2 attach statements. Right. And this allows us, almost like in the first one, we created a stack of Lego blocks. In the second one, we are attaching them together. That's the second part. But there is this other type of operation, which we call the squeeze operator, which allows us to sort of stretch and squish this Lego blocks. So if I do a squeeze operator between the two of the qubits, it sort of snaps to both ends. So the size of the cuboid and the middle cuboid, the blue cuboid, can change in this case. And there is an explicit symmetry relation, which is the reflect relations which support along with the rotational one that is also enabled in this domain-specific language. The way we have designed it is it's differentiable, so we can differentiate through the operator and the parameters. That's quite handy to do. So complex looking objects along with their structure can be now encoded into programs. So what we have done so far, we have taken the partnet, we generated variations using structured net, we converted them into graphs, and then we have rewritten the graphs as programs in this domain-specific language. Okay. Now we can benefit from all the work we have done so far, because we can create a VAE at the space of programs. And the programs, when executed, gives back the shapes. Right? How does the program VAE work? It's again a hierarchical one, because we use the hierarchy in the structure net. And in each level of the hierarchy, it's a sequence encoder and a sequence decoder. And the natural choice here is a GRU approach, GRU approach, to execute out the individual lines. In hindsight, a transformer might be a more relevant one right now, because it allows us, it would allow us to do a far further looking into previous codes to help in prediction. But what we did for this work is a GRU version. And in the decoder one, it's again very much like the hierarchy encoder and decoder we showed before, where we have a truncation condition where we have reached the leaf level. Otherwise, we decode out these lines. And then we compare the loss at the level of the programs, both at the whether we got the operations right and also the parameters right. We give more weights on getting the operations right, which are whether we got the cuboids right or the attach right, because we can recover from slightly wrong parameters, as I will explain later on. So once we have this, again, we can sample from the latent space. We can generate new instances of shapes, as you see on the middle row here, the ones in blue. And on top and bottom, we respectively show the closest or the nearest shapes in respect to geometric similarity, and the bottom one with respect to program similarity. And this is to show that the VAE indeed learns new shapes and not only memorizing the input. When we compare to 3D PRN, that's a competing method, you can see that because we have explicit handle on the structures, ours, which is the middle one, gives much nicer and a regularized shape. And here, there are two things that I want to highlight. The reason ours is better is once we have access to the hierarchy. And the second thing is because we are working in the domain-specific language, the language itself regularizes the problem and helps in the decoding and keeping it much more plausible in the shape of valid shapes, in the space of valid shapes. We can interpolate, and here's the bottom row is ours in this case, where it's an interpolation in the space of programs. And in the top row, it's interpolation in the structure net, which is the earlier part of what I spoke about. This allows us also to do program edits, so you can directly edit the programs and then execute them. And here's one evaluation that I want to show, which I think is a very interesting aspect of what is going on. It shows that how much of the shapes can we explain by having only a percentage of the program correct. So the more the curve is on the top towards the top left, that means a little bit of program already helps to explain much of the variations in the shape. And if you see that something like the table is explained very well by canonical programs, but something like the storage one, which has a lot of variability, then the geometry requires a lot more of the program steps to be explained. Finally, you can also encode point clouds directly because it's essentially an encoder of the point cloud to the latent space, and then you can decode with the shape assembly decoder. And this is better to optimize because we have a differentiable program right now over optimizing in the structure net space where it doesn't have the benefit of being regularized by the structure of the DSL. As limitations, we still have this handcrafted DSL, which we believe we can remove, but and it produces these abstracted shapes, but it requires this supervision in terms of the hierarchy information, which really is a limitation that such methods have. And the final thing that I do want to highlight, because that's an open problem right now, our VAE is working directly in the space of programs. And if these programs are not executed, in a differentiable way inside the training. So it may be that the final program, when executed, gets stuck or does not produce a valid output. Okay, so far what we have seen is what we can do if we have available 3D data. Now, one question we have been recently asking is it possible to work without the 3D data, but some data that is much more easier to obtain? And it started with this work that we presented last year, where we asked a question, which is not a new question, it's a very old question that Plato has asked, that if we have only images, or at his time, images on the cave from some light source, can we say something about what are the really 3D objects or the 3D world that casting these shadows? And this allows us to work without having access to direct 3D data. Right? So one way we can solve it is by looking back into our computer graphics background, which tells us that the way images are formed is we take in 3D model, we take in camera, we take in material and illumination, and out comes an image. And this image formation model is very well understood and can be written down with various level of approximation to produce images. So these functions are known, and we are not going to optimize them through the network. We are going to optimize for the parameters. So that's the main goal here. So let's quickly visit some of the image formation models we have. So imagine we have a grid of voxels where each cell is occupied or not, and that's indicated by the value vi. Then just the silhouette of it, the visual hull, is given by this expression, which is 0 if all the vi's are 0. If all the vi's are 0, it's exponential of 0, so it's 1. So 1 minus 1 is 0. As soon as one of the value is non-zero, we will start to see something. We have the absorption only one, where if all the values of vi are 1, then this value will be 1. But as soon as there's a non-1 value, there will be the row value will change. And then we have an emission model, which also allows voxels to emit light. Okay, this allows us to create what we call the Platonic GAN, where what we start with is a 2D image, which we have many as training examples. We encode them into a latent vector, and the generator outputs a voxel grid, directly outputs a voxel grid. And then we have the rendering layer that produce rendering from an arbitrary view, and then we can use a GAN to check if it's real or not compared to the images of chairs. The insight here is this module is known, and we make changes to make it differentiable. The generation process directly creates an output of 3D volumes or voxels. It's no longer supervised by the 3D volume, but it's generated as an intermediate step, and it allows us to train into a GAN setup. And in the next few slides, I will show variations and improvement of this, where we are spending increasing amount of effort in designing the network so that, one, we can avoid explicit 3D information as supervision, and two, we can use our graphics knowledge and the parts we are very comfortable with, right? The rendering equation or the camera projection matrix, we explicit write them down rather than require the network to find them, which we already know or have very good approximations of. One thing I want to highlight in the pseudocode is the sampling the viewpoint is a challenge and often leads to a problem in this method, because the most common view sampling you would do is uniformly over the sphere or half a sphere. But often when we capture real images, we have a very strong bias in certain view directions, and this imbalance between the two causes problem in the convergence behavior. There is a scope of making this view sampling also learnable. That goes a bit beyond of what we have so far successfully achieved to train. So Platonic GAN removes many of the previous assumptions, whether requiring template, known camera, known view, etc. Okay. So in this case, the black silhouette lines are the input images, and the pink voxels are the reconstructions that we got without ever requiring 3D training data provided to the network. This is case of chairs, and this is case of guns. Look at the numbers. There's a lot of numbers here with various competing methods that, as you multi-view, explicit 3D GAN requires explicit 3D, PR GAN was an earlier motivating work. But if you see ours will win, again, visual hull, absorption only model, and emission absorption, PR GAN does better than ours. But for the other two, ours is doing better among these methods. This is already a bit old because 2019, which is last year, but at the speed at which research is going, this is quite old by that thing. And there have been several follow-up works which have improved this method even by significantly over the last year or so. It allows us now to train on very esoteric classes. So we have this mushroom class that we have, and it allows us to generate 3D structures out of it. I wouldn't call it structure, 3D voxel representations out of it. Okay. Now, this is still at the scene level. And what we have since done is we have been more interested in going at an object level description of what's going on. So the goal is, can we go directly from images in an unsupervised way to enable object level control? Let's look at some of the motivating literature that I think is one of the most exciting type of research going on in this overlap between graphics and vision and machine learning now. This is this HoloGAN paper that was presented last year at ICCV, and this scene representation network, which was also presented last year at NeurIPS. Okay. Let's look at the HoloGAN output here. So what they do is quite similar to Platonic GAN in spirit. So what it has is a generator that takes in the latent variable Z, produces image, and there's a discriminator to check if it's real or fake. But one of the very clever insight who had at this work is she explicitly introduced this parameter theta to control the camera model. So the camera model was very explicit, and it's an explicit quaternion or a 3x3 rotation matrix that is being applied in the theta one. So what the network is doing is it is free to learn features at each of the voxel grids. The rendering layer is learned, unlike the Platonic GAN, but the movement of the features under rotation, that is explicit because we know the rotation matrix. And that's a very interesting insight. What HoloGAN, however, stops at, this is a rotation of the whole scene. So if we want to do object level control, we are stuck and we cannot do. And that's what we enable with our latest work on BlockGAN. So let me explain this motivation. And again, we go back to our graphics background to see how we have objects and how we can do individual object level interaction. And these objects, as we know, are often represented as hierarchy of parts. So what we have is, again, an inductive bias in how we structure the network. So we have a background layer. We have several foreground layers. Note that these are not alpha masking composition. This is exactly objects in 3D or object instances in 3D. Each voxel is allowed to learn a deep feature corresponding to that object. The theta I, that controls explicitly the location or the transportation of features of the voxels. The scene composition function is learned. I would refer to the paper to the 3 types of composition function we tested against. And that allows us to go from object coordinate to scene coordinate. Explicit camera control, very much, this step is very much like HoloGAN, allows us to go in camera space known camera projection unit, similar to Platonic GAN, creating images directly. Now, I want to stress again, the scene composition is learned, the camera unit is fixed, the object level rotation, object rotation matrices are known, the deep features are being learned, and the only supervision is a set of images only without any explicit labeling. Any decomposition of layering of here's the background, here's the foreground, that's all being learned in the network. As comparison, Hologan had one monolithic block for the whole scene. Okay, so here's a nice illustration of how the training works. Z0 is the background. So here we're changing up at inference time, we're changing the foreground, changing the background, moving the foreground object, one of the foreground objects. It allows generalization. We can add new objects, and we can of course rotate them and others. Let's look at how this would look on different data sets. We have a synthetic data set of chairs, synthetic data set of cars with highly specular cars on the clever data set, and we have natural images of cars. Not that we have very small images, because that's what we can handle so far, 64 by 64. So on synthetic data set, we can allow rotations, as you see on the left. So each object has an individual rotation handle. In this work, we assume we know the number of objects. Here, we are moving individual objects, translating them. I would like to bring your attention to a couple of things. So please note that as we are moving the objects up and down, note the complexity of the shadow on the ground, and also note how the specularity of the reflection is moving along with translation and rotation. And this is completely unsupervised. Here's on the chair data set. There are blemishes you would see, but again, you see some things that are very hard to get in other ways, like the complexity of the shadows you would see on the ground. And here, note the perspective effect that we are getting by just modeling the camera and having the features move back and forth by where they end up on the perspective grid. Results on natural images. So here you'd see the cars being rotated. And if you look closely, you'd see artifacts due to bias in the sampling of the views, because some views are better represented than others. Here you see translation effects, just rotating by keeping the background fixed. You see we can also scale the car up and down or axis align, or we can also change the foreground object, the appearance of it by changing the latent vector for that. Comparing to 2D methods that allows object level control, but at the level of composition, the C function, as you see on top, with the separating into background and foreground. Here's three comparisons I'll show. Changing background object. The top row is the LR GAN, and the bottom row is ours. You see on the top row, it's not rightly disentangled. Hence, when we change the background or attempt to, the foreground object also changes. In the lower row, you can see ours preserve the foreground object much better. Here you can see changing the foreground object. So the background should remain fixed. And again, ours does better here. And adding objects, which is a generalization behaviors, ours does much better because it allows, it captures this directly in the way we have structured the network. There is a big limitation, though, of this method, that we assume that the objects are treated independently. Hence, when we have objects which are closely related, for example, here you see a stack of objects or blocks placed together. When we ran BlockGAN, we found that everything gets mapped to background. We don't get the decoupling into the level of objects. This motivated us to explicitly model the relation between the objects and having a unit on this. So we are now doing object level, but also there's interaction between these objects. So as you see in the car case, the cars are moving in the straight line or turning around, but they also slow down or speed up depending on the distance of the cars or how the objects are relatively placed. It's quite simple dynamics, but still difficult to learn in unsupervised way. So bottom one is the block GAN architecture. And on the top one is the relate architecture, where the main change is this interaction module or the learned interaction module, which is realized as an MLP. And all this MLP does is takes this theta I hats, which are the individual object as if they are independent, and learns an interaction modules that maps the theta I parameter or object coordinate parameters into in theta I hat parameters and maps them to theta I without the hat. Right? And that's the sort of retargeted positions that considers interaction. So for example, in this illustration, the orange and blue dots are independently generated on top of each other, and the interaction module sort of separates them and pushes them apart. So that's the goal that we hope that this structure is enough to allow for these interactions. And we do it in a Markov chain fashion where later objects only depend on previous objects. And that's explicitly what this equation is showing. And we, again, realize them as two MLPs, the FMLP and the HMLP here. This allows to create this ordered scene where we have ith object depend on the previous objects here. So in the stacking example, the bottom object is the first one, the second one depends on the previous one, etc., etc. In this work, unlike block GAN, we relax the assumption that we have to know the number of objects in advance. So this we can handle now by having the option of objects turning out to be empty. And now, as you can see, compared to the block GAN thing, that it correctly decouples the background from the foreground. And again, this is completely unsupervised. So although the pixel resolution is very small, it's still a very exciting result that we can do this. It allows us to model dynamics because now the interaction is in time. So the t plus 1th instance should depend on the object location of the previous one. We encode this by a velocity vector v. And once we have a v, we have a first order model, add the v to the previous object location to get the updated location. So for this example, imagine this is a synthetic, like a ellipsoidal ball with two balls rolling on the ball. And you can see here what the network produced, which are given by the red and the blue crosses, showing how the path of the ball should follow on the ball. Look at that the paths are quite nonlinear because it's trying to follow the profile of the ball. Here's the car example from left to right. We're moving further in time. And if you look at these examples in the extrapolation, it does nicely even allow the green set of crosses to sort of rotate, not rotate, the car rotates into the side street, which is quite nice. It allows us to do object level manipulation, very much like block GAN. It allows us to change one object, add objects, move objects, etc., because now we have explicit handle of the position. And here you see the original sequence. So that's an input sequence from a video graph of a signaling light in one intersection. And here you see the synthesis results, where we can now extrapolate sequences, change the speed of the cars. Some of the cars, the fourth row, you would see that the car is rotating. Sorry, the last column, you see the white car is rotating into the side street. Okay, so in the last few minutes, I want to just touch on this final question that I have and started with is, do we even need explicit 3D? And this maybe relates nicely to the title of my presentation today, which I call the deep 3D 3D modeling or 3D generative modeling, where the deep part is maybe we don't want explicit geometric representation, but enough to do a deep representation. And that is sufficient for many applications as long as it allows the user to control. And control can be, depending on the application, I want to move the objects around, which we saw in Blackgan, or relate, or I want to change the illumination, I want to change the expression of the person, etc. Which brings to the last part of my talk, which is style flow, where we were surprised that such a result even produced something that is so compelling, because at the beginning it was more as an experiment that we started with, where we were very much inspired by the success of StyleGAN on producing extremely realistic images with a lot of diversity. But then we asked the question is, suppose these are given, and this can be on cars, this can be on faces, but the question we ask is, can we now have explicit control? Note that we are not going to do a conditional GAN, but many people have tried, but what we are going to do is a conditional exploration. So we would only explore the results that StyleGAN found, but it has to be non-trivial paths in the StyleGAN parameter space. And what we want to enable is we start with the real image, we project it to StyleGAN space, and then we would like to progressively edit it. We change the illumination, so move the light from the left, looking at this girl, change the pose of the girl, change the age of the person, or change the expression. Okay. Notice that the identity of the person we would like to preserve. And by that, by preserving identity, we mean all the other attributes, and it's from a set of listed attributes that we are not changing are preserved. When illumination is changing, pose is not changing, or age is not changing, expression is not changing. So it turns out to be a simple design, but it's not the first thing we thought of when we tried doing this. So what we have in StyleGAN is we start with a weight vector that gets thrown into these add-in layers, and then we get this updated weight vector, the 18 parameters or 18W plus parameters as they're called, which when decoded gives an image. But what we care about are attributes or control knobs for these images. So we train a set of attribute classifiers that gives us attributes of this image. So now we are deviating from our original goal. It is supervised, but it's supervised in the image space where we know whether the person is smiling, maybe the gender of the person, the age of person, etc. And now we can do a conditional control, but again, it's control rather than conditional generation. How can we enable this? We can go from our weight vectors, which is denoted by W, but it's a very long set of weight vectors. And then we want to learn a bijective map that takes these weights and attributes and outputs a new latent weight Z. And we realize these this one by a CNF, which turns out to be this normalized flow, turns out to be a really good model for having the bijective map, and the stack of them allows us to do a really complex mapping while preserving the bijective nature of it. Okay, that's a reverse encoding. But at edit time, now we can start with this original image. We can retarget the attributes. So I want to change maybe the expression or the illumination of it, and I can go the other direction. Remember, it's going to be on both directional, get the updated weight vector, and then re-render it through the fixed StyleGAN layer to get the edited image. And that's a level of detail I will provide here. I'm happy to talk more about the details here. But the key here is having the access to the attribute classifier and training this bijective map that allows us to go from the W to the Z. Okay, now I'll show you a couple of examples just to show how compelling the results can be, and that allows us to or prompts us to really rethink how this this interface between graphics and vision should look like in a couple of years. So these are two images, and here you see the quality of the edits. We are changing the illumination. It's surprising to forget that we do not have the 3D, because you can see the fidelity of the input, and also the fidelity of the control in how well the features of the face is preserved. If you look at the features of the hairlines and others, I'll replay it again. So if you see here, look at the quality of the shadow, the crispness of the shadow as it moves. And also in the next example, you would see the hair quality and others. There are changes, the background changes, but it's really something that would be, I would not know how to achieve it in any reasonable time on a projected image using a standard graphics workflow. So at this point, I would like to summarize what I presented. We mainly focused on three questions among the main challenges I see in terms of enabling really deep 3D generative setup. We talked about the importance of structure, both at the level of part graphs and at the level of programs. We talked about the opportunities in unsupervised setting, both at object level composition and relation between objects. And finally, we also had this rather perplexing result that we can directly control a learned GAN space to get 3D control without ever creating or authoring explicit 3D. So with that, I would like to conclude my talk and would be happy to take questions and go into the discussion. I would encourage you to go to our website for code and data. If anything does not work, please let us know. We are always excited to talk about 3D and to look at the latest research and together push the field forward. And I'll also take this opportunity to thank the many, many collaborators, students, postdocs, and other researchers across the world with whom we have collaborated, and that's largely resulting in the work that I presented today. Thank you.
Thank you very much for the talk. The results are very impressive. I looked at it; it's really impressive to see what the level of detail is that we can get there nowadays, especially compared to where it was in the last few days. We actually have another person joining, which is who is Andreas Geiger. Andreas is a full professor at the University of Tübingen and is also part of the Max Planck Institute for Intelligent Systems. And he will join us for a panel discussion. Before we start the panel discussion, there are a few questions on YouTube that we could maybe answer briefly. One of them is a question of representation. So, for example, for the Platonic GAN, would you get better representations if you would replace voxels with implicit functions or meshes?
I think it's great that Andreas is on the panel. I think he can answer the implicit surface representation. But yes, there are opportunities in going from voxels to other representations. So we have a paper at ECCV where we used a more like a mesh-like or a surface patch-like representation. There's a work from Yaron's group on implicit surface and materials, and doing this here. That does at least the last version I did see requires some information about the camera calibration, which Platonic doesn't need. But in general, I think there is a lot of interest now in sort of looking at the representation aspect, whether it's SDF or occupancy net and others, to see how we can combine this to the Platonic GAN part, or this, and more generally in the unsupervised setting where we don't have direct 3D supervision. The question of representation, I think, would just go on. I do not think there is a final answer here. It just depends on the application and where the optimization is better suited.
I mean, Andreas, feel free to comment if you want to say something, right?
Yeah, I don't know. I might shamelessly advertise our new NeurIPS paper, which is basically doing like what Platonic GAN is doing, but with an implicit model. So we have a model that's basically built on this neural radiance field representation, which is typically like the implicit model that is fit to a lot of images of a static scene. And so, but we are looking at it from a GAN perspective, so an unstructured, unposed collection of images. Like holoGAN or Platonic GAN, and trying to generate like a generative model. And it works surprisingly well. You get like very detailed depth maps out of it, even for you don't have this at training time. You don't have any paired images, but we have gotten it to work at the moment only for objects. So that's kind of I think going to scenes and at high resolution to scenes is still kind of an open question, but at least at the object level, it seems to be quite feasible at the moment, I think.
Which actually I think leads to a very nice follow-up question, which is, so far we do simple scenes like static background, couple of objects moving in the scene. How far away are we from much more complex scenes where illumination can change, where actually objects or actors might interact with that scene? Is the type of technology that we have at the moment, can we get in that direction, or do we need something fundamentally new?
I can start with some thoughts based on the type of research we are doing. So animation is one aspect I did not cover in this talk, but we have some initial results there. You can look on our website for this, where we also try to have a neural model for the animation part so that we can drive it. We're particularly fond of looking at garments and how garment motion and secondary motion can be controlled based on body joint motion, which many others across the world are also looking at. Now, there are a few fundamental issues there. One is even state-of-the-art simulators, differentiable or not, has challenges with very high scale or very, very detailed 3D geometry, because there are numerical issues that sometimes things just blow up because we don't have the explicit one. The second challenge is we often do not have full resolution geometry for at the fabric level or other levels. And that sort of nicely links it to the opportunities that neural rendering and others allows us to avoid explicit 3D, but allow us to hide some of the details in the rendering layer or the learned rendering layer. So yes, there's a lot of opportunities there at the level of human actors and their control paths. There is quite a body of work, not in our lab, but in others who are looking at control dynamics for humans. It would take a few years in my understanding for these things to come together in one coherent system. But that would be the dream to have.
May I also ask a question? So you have presented this, you have done great work in both of these aspects, in like primitive-based reconstructions and like reconstructions that don't require an explicit 3D representation. So do you see these two somehow coming together? Like, do you see where these at some point will merge?
That's an interesting point, and maybe I'll quickly take this time to just go to a visual that might be useful here. And often I get inspiration by looking at how computer graphics solves it or how artists would solve it. So if you look on the right one, the parametric geometric model, so what we see here is very complex geometry, but some of it is created procedurally. So there is a language in the space of materials called substance that is essentially a composition graph of operators, which you can differentiate through. And that creates different layers. Some can be displacement maps, some can be normal maps, some can be albedo, etc. So even I think that might be the right sweet spot of having a hybrid one, that the geometric part or the generative part creates a base model, And then there is a parametric part that takes over. And ideally, we would like to backpropagate through both the geometry layer and the parametric layer. The reason I'm a bit skeptical of geometric details all the way to the end is probably because of my long history in this area. I have seen so many years, so many decades maybe of people working here. We haven't hit the ground where it's something that really we can make it work. Also, unless we're really fabricating it, why do we even need the explicit geometric layer details at the very fine layer if the rendering only needs to work at the level of at an intermediate level? So that's my current thing. But if there is a paper tomorrow on arXiv that shows it can be done, I would love to switch over to that. But it's not a high chance in my assessment of that happening.
I think in this context, an interesting question is, so you had these scene graphs and you had the programs, which are very much loved. How complex can these programs become before the whole training procedure starts to break down because the network can't go through it anymore?
Yeah. Let me go to one of the programs. One here. Yeah. So I think this is in very early stages, this program synthesis part, like for a couple of reasons. One is this assumption that we handcrafted this language. That I think we already are working on it, and I think that we would be able to solve, or others would be able to solve. But the part that is difficult now is because much of the work is inspired by advances in program synthesis and NLP, that it still operates at the level of program rather than looks at the execution of the program. And certain things that I did not have time to talk about, that certain lines of the programs can be switched and the output would be same, etc. That adds to complexity. So like a big step in rendering has been the differentiable rendering. Big step in simulation has been differentiable physics that we have also done. But we do not have a differentiable execution of the shape programs yet that we can backpropagate through. So that's one complexity right now of how far we can go. So we hope that we can push the boundary, but there needs to be a fundamental change in the execution has to happen so that we can directly have the loss on the geometry rather than the program. So that part is missing. That's my assessment right now. But again, as you know, there might be a paper as we speak on arXiv that handles it, so that can change our understanding of this area.
So maybe I can also ask one question here. So how do you see the relationship to autoregressive models? I mean, autoregressive models, they are fully differentiable, and they have shown like interesting results in a number of applications, like generating pixels, but also generating scenes. So how do you see kind of the advantages and disadvantages of these autoregressive models versus like this program-based synthesis?
Definitely, I think that's something we had considered with Pixel CNN and others when these came up, and I think that's a lot of excitement in that way. The one thing I think where the program is interesting, there's two things I want to say. That's why I think we wanted to explore the program direction, and we are doing it now. One is the program itself regularizes the problem, which is not a type of regularizer we have as access to otherwise, right? And this can be coming from the choice of data set, choice of others, but I think that is a strong regularizer that is hard to mimic in a geometric way. The second thing is, I think the program allows us to have an abstraction that that can couple things that looks very geometrically different, because that's how procedural modeling works. So if you look at L systems and other things that has a long history in organic shapes, in trees and botanical structures, there, although the final shapes are very diverse, the set of programs explaining them is much more compact, and that allows a much more expressive latent space. That's the vision with which we started. Now, whether that's really necessary and can be instead done by something working directly on the geometry level. Currently, I would say program has the advantage because of these hypotheses we have. But that's the best answer I have about this. I'm also torn between the two words. So I have my gut feeling right now, but I don't have a better reason to explain why the program one is fundamentally stronger than others, other than it has been shown to be much more expressive while being compact.
Since Andreas brought up autoregressive models, so what I love about this is the connection to human language. And there was OpenAI's GPT-3.
Yeah.
Have you thought of training one of these things to just automatically generate the program and then just execute it?
That is a really cool question. So we are looking at, in the concept of materials, so the ones that the visual I had before this, where we look at the substance graph. So we are doing, right now we are working on a language-based approach of creating directly these programs for substances or materials that would produce this. The complexity is these graphs can be often quite big, spanning hundreds or many hundreds one. So that's one complexity in terms of how the number of nodes changes. The other thing is, because the training data is hand authored by artists, they're limited. So they're order of few thousand, not in terms of millions right now. So one thing we are trying is, can we again do what we did with Platonic GAN by replacing the need for 3D supervision to go to like the image level supervision, but it's turning out to be quite difficult to get it tamed as we see right now. Right? So, but that is the vision, yes. So we're trying to do that type of an approach.
Talking about training data, so since artists also use some sort of, sometimes use some sort of scripting language, would it be possible to learn, like do it in a two-stage procedure where one stage learns like a reasonable space of parameters for the scripting tool, and then use this to generate data for an generative model?
This is really love the question. I think that's something I believe is the way to go. My answer would be in two parts. I'd use this chance to advertise one of the papers we have upcoming at SIGGRAPH Asia, where we go from sketches to a scripting language in a CAD setting for creating the CAD models. So you draw, like, say, a camera, and you draw the strokes. It says, oh, here's an extrusion of a cuboid, here's a cylinder being added, here's like making a bevel operation, etc. Now, it sounds like we solved the problem, but unfortunately, it's only a partial solution, because we solved it on data that we created synthetically. The real one would be if we have artist data or instrumented data on a CAD system. Now, I have been talking with a couple of top 3D modeling companies for the last couple of years now of trying to get this data set. They have the data set, which is good news. The bad news is when they collected the data set, and these are from amateur users, not from super users, they did not have the right permission. So it's really down to the lawyers if they can enable it. But that's a question of time before such data sets would be available. And then I think we would have a whole new set of problems to look at. Can we directly learn from these scripting language? With synthetically created data set, we can only go that far, at least currently, what we stand, because it's kind of a chicken egg problem. Like, once we have the first part, we can influence the second part, but learning both together, it's probably okay to formulate, but it'll be difficult to get convergence. Yeah, but that's really a very, very interesting direction to look at. Yeah.
Andreas, I would also love to hear your opinion on this, given that you traditionally come from the direction of building 3D reconstructions, obtaining data from images and other sensors, and then using this potentially for training generative models.
Yeah, so I have less experience in that area that Niloy was mentioning. I think like what would be interesting for me is to do something that requires as little supervision as possible, right? I think it's a great idea to have these inductive biases through these processes that we know, but some of these might be wrong, right? So you want to commit only to the things that you know are correct, like the image formation process which we can model, and maybe certain physical processes that we know about that they are correct for sure. And ideally, the rest comes from the data. Now, the question is, how does it come from the data? And I think really the challenge is to go from the object level to the scene level. Like we know that we can build generative models for images and for 3D objects, and they're getting better and better. But I think what we really need to exploit more is the compositionality of scenes, right? So that we can get models that kind of automatically decompose the scene, and ideally without having humans annotating path hierarchies or relationships, etc. So I'm not sure exactly like how we would go there, but I think it will be kind of an interleaved process where we build machine learning models that maybe at a more abstract level understand scenes, and then on top of this we build models that basically lead to realistic renderings of these scenes. But this is somehow an interleaved process where I think it's fine to go around and collect data. I mean, all the data that we can easily collect, we should use it. But whenever it comes to annotations, we want to be as self and unsupervised as possible. And I think that's kind of the holy grail of scaling this up to all kinds of scenes, indoor, outdoor, like kitty-like scenes, like building a good generative model for the kitty data set. I think that's something we haven't achieved or we haven't even come close to. That is both geometrically accurate and photorealistic and allows for generating new scenes, for instance, right? So I think that's still something that that requires a lot of innovation. And also in terms of the representation, like these implicit models are great, but of course we want to go beyond the object level alone, and we want to have models that are realistic at the city scale or at the building scale for indoor scenes, and this doesn't work out of the box with the existing representations, because you very quickly get to also the memory limits. And so I think one key, coming back to this, is exploiting compositionality and defining like models with implicit biases that are kind of mild, that don't impose things that are potentially harmful, but that are powerful enough to lead to this decomposition. While I think, on the other hand, I think it's fine to use, and this is also a trend we are seeing right now, to use models or information that is there, or models that work well. Like, if we have something that is a good saliency model, I think it's fine to use that. If this can provide inductive biases for segmentation, for instance, right? So we can use these models, and we probably need to use these models.
As a follow-up question, I mean, one thing that I'm wondering is how much are we limited by static data sets, in the sense of we have a one-off recording, so we passively consume data, versus a human that's actually able to have some sort of understanding of the scene and then verify this by looking at it from different angles or interacting with this. Do you think this is a limiting factor?
And maybe I just want to link to something Andreas mentioned in the previous comment. Sure. Is if you look at these results, I think that there are some things where the complexity of the problem quickly is quite daunting. If you look at the shadow on the ground of the car, right, or the reflections on the car, we see from this one, how much we need to explicitly model, because this is not like a layer-wise interaction. It's really the 3D interaction. Do we need to model this in 3D? Because if we have to backpropagate through radiosity, that is going to be not the easiest thing to train. right? If we want to expect everything to work out of the box. So that's the question I think that as a research community we're asking now, like how much of this do we need to be explicitly modeled and how much we can leave it for the network and hope that regularizing the design of the network already fixes this. I think that's how I interpret Andreas' comment about this.
I agree. Yeah, maybe for Torsten's question. So I think I think we need to go back towards like active exploration and looking at. And I think the community has realized this. This is not a secret, right? It's like since a couple of years, there's these efforts towards like combining robotics and vision again, because like just working with static data sets doesn't lead us to the ultimate goal. So we have these exciting advances with the Gibson environment and habitat, and also what we are using a lot is the Kala simulator. We're using it both for vision projects, but also for sensory motor control projects, where we're trying to really build agents and learn policies that are robust and generalize well. So I think this is exciting that we have like more and more access now to, which wasn't possible before, right? We had very impoverished simulations that were very far from the real world. Now we are getting more and more simulation data, better simulators, and that's great. Still, there is a gap, of course, between what we can simulate and the real world. But I think like people have realized that we need to bring this together. And for instance, also in the habitat environment, there's now environments that come from real scans like Matterport or replica data set. Which I think is exciting. If we push this more, I think in maybe coming back to my earlier answer, in this iterative process of creating better simulators and learning better models, and using these better models to create better simulators, I think we can scale this up, right? We cannot build simulators just by having a team of artists. I mean, that's what Kala is doing effectively at the moment. And it scales up to a certain extent. We have now 10 cities, and we have better 3D models, more realistic assets. We have 50 types of cars, and that's great. And we are at a level where this poses real challenges now again for the self-driving community. And until we have solved them, the simulator is fine. But eventually we'll solve them, and so we need even better simulators. And I think with such an iterative process, we can potentially scale this up, and I'm very excited that this is happening now and people have realized it, and also everything is available as open source, which wasn't there just 5 years ago.
I think this visual that we have on the screen, I can use it for this active probing, because that's a problem that I mentioned, and it is something that we haven't addressed yet, is when we work on these natural images of the cars, the car images, people like to take it a bit off by what we call plus minus 40 degree, because that's where the car looks nice rather than the back and the others. So there's a very strong view bias. So either that comes as an output of the method, and in an active setting, we send out some sort of a sensor to capture more from the other views. But that would be one way to know, like at least in which views we can be confident that this is a reconstruction versus or this is a plausible generation versus we just don't have enough data. So that's actively probing for data is also a version that Torsten, your question links to.
I think one important aspect is also to add here is what task are we actually solving, right? Are we interested in creating photorealistic renderings for virtual reality, or are we interested in programming a robot such that it behaves robustly for certain maybe manipulation tasks or a self-driving car? And so depending on the answer to this question, the algorithms and the models that we need might be very different, right? And so, for instance, if we are interested in visual quality, we still don't have the gold standard metric even to measure photorealism, right? We know that like standard simple metrics are not good at measuring photorealism, and we have developed better ones, but they still have issues. And so the question is really like, ultimately, what are we optimizing for? And there's, of course, I mean, there's a whole variety of applications we might be interested in, but depending on the application that we are interested in, these these requirements change, of course.
Maybe so. The vision in the end, in your talking here was in the beginning was that you would like to make it easier for artists or potentially replace artists by using AI. And you showed those models that really take a long time to model by hand. How far do you think are we actually from going there and creating models of that level of realism, of that level of complexity?
One thing I want to very, very clearly mention, I love computer graphics and I love this one. So I'm not in the business of making artists obsolete. That's not the goal, right? So that's clearly not the goal. It's to make the exploration process much more simpler. Right? So in this case, I think if you look at this sheet, at the static level, in terms of textures, we are, I think, auto suggestion of texture, autocomplete of this procedure. I think they are quite far along. In the part where we have to physically model the physical behavior and under collision others, I think that is still very heavily artist dependent right now. At least I'm not aware of workflows that allows that to be easily authored. One can think of state machines for doing this, but these are quite like maybe 80s game, 90s game, not the realism that people will expect right now. The vision that we have, and that has been our focus, is we want to take over the manual part needed for modeling the secondary assets or the secondary behavior. The primary assets and the primary behavior should still be done by artists, and then they have more realism on doing this, because the secondary assets often takes only a few pixels in the screen, and it's not worth their enormous amount of effort and time and skill to do this. So that's the vision we have. There is no generic answer here because it's very, very application and scene specific. For movie, there is one type of budget, versus game, there is a different type of budget in terms of number of cycles available, how quickly the game should run. So all I can say, we're quite a bit advanced compared to 2 or 3 years back, but still a long way to go in sort of making this much more streamlined. Because they're still using Maya and Blender. That already shows that we haven't quite succeeded yet.
Andreas, what's your thought on this? Because
yeah, I agree.
okay, yeah. So traditionally, this is the time where how long we took for the last few seminars. But I don't want to interrupt anything. I'm happy to continue this if you want to discuss things in more detail, or if you have talking points that you would like to open up.
I think if we continue to talk, we can talk for many hours, because there's a lot of shared interest and a lot of relevant problem that needs to be solved. Unsupervised is a big frontier moving forward, and animation also came up as being here. And as Andreas mentioned, I think the application is always something that should be driven here, that should determine, yeah.
Yes, I agree. I mean, there's endless open points for discussion, for further discussion. But I think maybe we can conclude here. Also, I need to get my kids from the kita, and yeah. I think it's maybe I can just say it's a very exciting time, because like at the same time it seems like we haven't made a lot of progress. It seems like every year there's a major breakthrough in the field. There's still like a lot of very fundamental unsolved problems, it seems, right? And so this is, I think, is an exciting area to be in, and many of the ideas that we are like looking at today, they have been around since the last 20 years, right? And so it really means like we're working on really challenging problems, and it's exciting to see how this goes forward with the current speed of the field. And yeah, so thanks also for inviting me here for the discussion. Was a pleasure.
Yeah, thank you very much. Thanks, Niloy, for the fantastic talk. Or did I interrupt you? Did you want to say something? I'm sorry.
No, I just wanted to say thank you to Thorsten and all the organizers, and also for Andres for making the time. Thinking it's at least one of the nice things right now, because in COVID, every country is different, every place is different, but at least we still get to see people and see exciting works going on. So something to look forward to.
Yeah, thank you very much for being part of this. I really very much appreciate it. Thanks for the interesting discussion. Yeah.